In this problem, we are given a sorted array, and we need to return the index of the target value if it exists in the array, otherwise the index where it would be positioned. And the algorithm must be in O log n runtime complexity, and this almost always means that we need to have some sort of divide and conquer approach, and this problem is a classic binary search problem. So instead of searching every single element in the list, which would be O(n) in linear time, we want to kind of divide the problem into half each time. So we would initially start by looking at the value halfway, and then if the value at that halfway point is higher, then we would look in the second half. If it's lower, then we would look in the first half, and then we would keep dividing the list until we reach some point. So we will have some starting index, and the starting index will always be 0. And we need to know what the length of the list is, so we can do length of nums. And so our ending index is going to be the length of nums minus 1. And just fix, okay, so we want to kind of keep recursively halving the length of the list until we find the target value. So we can keep track of the current middle value, and that'll just be set to none, and then the current middle index, and that will also be set to none. And then we want to keep going until the starting index does not exceed the ending index. So we will recursively keep going to the halfway point, but then we will be either adding one or decrementing one based on whether or not the value is higher or lower. So we would want to have a while loop, and so we can say while starting index is less than or equal to the ending index. We want to kind of find the halfway points, and we can initially always just return, and we're always going to be returning what the starting index is, since the problem wants us to return the where the value would be if it was sorted. So that would always that would not be the middle index, because that would be too far. So the range that we're looking at is always the kind of starting range that we will have to place the value in. Inside of this while loop, we want to find out what the middle value or the middle index is before. So we can set that, and the kind of logic to find the middle index is we want to sum up what the starting index plus the ending index is, and then we want to divide that by 2, and this double slash simply means that we are discarding any remainders, so it is only the quotient that we are interested in. And then we can find out what the current middle value is, and that'll just be in nums, current middle index. And now that we have the middle value that we are currently at, we kind of just have 3 cases. So the first case is where the current middle value is equal to the target that we're looking for, and in that case, we want to directly run the current middle index. And we were returning current middle index here because that is exactly where we are at, and so the starting index would be too low, and the ending index would be higher. So that is why. And then the other cases is simply where the current middle value is greater than target, and that means that we have overshot, and we are kind of restricting leftward, and otherwise it means that we have undershot. So if the current value is less than the target, it means that we need to go rightward, so we need to restrict rightward, and that basically means that the starting starting range is equal to whatever new middle index is. And if you are restricting leftward, it means that we need to shift the ending index to the left. So the new ending range is equal to new middle index. And so we can implement that. So if the current value is greater than the target, we want to set the ending index to the current middle index. And we want to add, for the other case, the starting index equals current middle index. And so in this current state, we will never actually break out of this loop because we are never going to have the starting index be greater than the ending index. And the simplest way to kind of break out of the loop is that we could have some sort of counter and then iterate that until log of the length of num steps. And because the optimal answer will always be guaranteed to be found within log n steps. However, that means that it won't be as optimal as possible because we might end up doing more pointless iterations. And so to make sure that we actually converge such that the starting index does eventually cross the ending index, we want to do a +1 and -1 on the ending and starting indices. So if you're at the ending index, we want to set that to -1. And if you are at the starting index, then we want to add 1. And this is going to lead to a convergence after at exactly like log n steps in the worst case, and in the best case, we will take even fewer iterations. And just walking through kind of the intuition here, when we are overshooting and we are trying to set the new ending index to whatever middle index you're at, remember that the middle index is not the target value. And so if we set it 1 less, that means that that is the last potential value that the target could be in. So we're not actually like missing any values here or like excluding any values. We are already covering the value at the target, so or at the current middle value. So we want to kind of do 1 plus or 1 less. So in the case that we're undershooting, our starting index is going to be at minimum 1 greater index than the current middle index because it did not well, the current middle value is not the target. So that's kind of why it works and why it's necessary. But know that the -1 and +1 and this sort of while loop is only necessary because we want to avoid doing log n iterations every single time. So this can be even better, right? So we want to kind of prefer this method unless instead of always iterating to login steps if the target is not in the nums list. But if the target is in the nums list, then either method will always find the answer in the optimal amount of steps. And this should be current middle value. And so if you run this, then it should pass all of the test cases. And this would be the most optimal solution in whole log n time. So that's all for this problem, and thank you for watching.